Another long wait. I apologize, but I said some stuff at the end of the last episode that I really wanted to clarify in my mind. I had rough sketches of what I wanted to say, what I thought was true, but I hadn't gone and worked out all the details, and now that I have worked out some of them, I would like to say that what I said at the end of the episode was slightly inaccurate, and I had known at the time, but I wasn't being clear enough. My definition of Sikorsky space is not equivalent to Sikorsky's definition. It actually has some features that I chose it specifically for. It actually can distinguish between some spaces that Sikorsky's definition cannot. However, every single one of my Sikorsky spaces is in fact also, it can be made canonically into a Sikorsky space in his original definition. So that's what I wanted to say on that front. I'm fairly certain that my Froelicher space definition is equivalent to the normal Froelicher space definition. I'm in the midst of proving that myself. But I'll come out and say that that is just something that I suspect, and I will, when I have the full details of that worked out, I'll come out and present to you the examples that I can distinguish with my definition, the proof that my spaces can be made into Sikorsky spaces, and also that whether or not my definition is or is not equivalent to Froelicher's in that case. So all that being said, all of the machinery, all of the axioms is essentially the same. The only difference is the way I have defined the set of plots and coplots. So you could go on and take their choice for sets of coplots and plots. In Sikorsky's definition, he only considers scalar valued maps, where I consider maps into any Euclidean space. And Froelicher also, he only considers scalar valued maps and curves. So those are the adjustments you can make if you want to do things in the original sense, but it's mechanically going to be very similar. So now that that's all said, I can actually get into proving some things and doing some work this time, and won't be just discussing different definitions in machinery. And to do that, I'm going to discuss what it means to be smooth, or rather what it means for a map to be smooth. We kind of said before what it meant for space to be smooth, that you're equipped with some sort of structure, one of the three that we've got. But for maps now, we've got three different definitions that come from the three different structures. So the first definition, that of being Serow smooth, it can apply obviously to anything that's got families of plots on both the domain and codomain in order to check. So it could be checked for Serow spaces, and you could also check Froelicher spaces, or maps between Froelicher spaces to see if they're Serow smooth. And the way you do that, to see if a map F is Serow smooth, is you take any plot from the domain space, from X, the first one, and you compose it with F, and if that gives you a plot in your codomain's plot space, then that means that this thing is smooth. That's what we define to be smooth. It takes plots to plots. So it takes plots for the domain to plots for the codomain. Okay, so Sikorsky smooth is incredibly similar. It does the exact same thing, except it's going to take coplots to coplots, and it has to reverse the order. It has to take coplots on the codomain to coplots on the domain, because of the way functions go. They go from the domain to the codomain. So a map F is Sikorsky smooth if for any coplot in the codomain's family of coplots, the composition on the left side is going to be a coplot in the domain's family. Okay, so those are the definitions for Serow and Sikorsky smooth, and they are very symmetric. They're very similar to each other. The definition for Froelicher smooth is not like them exactly. It's actually a whole lot more like the definition of smooth that we see for smooth manifold. And this is what you can kind of, if you remember, for smooth manifold, we had local representations. We had charts on the domain and the codomain that we could use to make a map between Euclidean spaces and then check that thing for smoothness. Here we have, instead of a chart, we have plots and coplots, and we can compose those with a map like this to get maps into Euclidean spaces. And if those are always smooth, then we say this thing is smooth. So a map F is Froelicher smooth if for any plot in its domain's family of plots and any coplot in its codomain's family of coplots, this composition, where I compose the coplot on the left side and the plot on the right side, is smooth in the normal sense. It's because it's just going to be a map between real spaces, some Rn to some Rm. So you just check it by taking partial derivatives and seeing that they're continuous at all orders. All right, so these are our definitions for smoothness. And what I'm going to do now, just like before, I don't remember if I got around to smooth maps. But if I did, then I probably proved a bunch of examples of maps that are smooth. I'm going to do that again because there are a lot of not a lot of examples of functions that are smooth that come up over and over and over again. It's going to be super useful to know that they're smooth. So let me move on to another sheet of paper and show you that. So the first proposition that I'm going to prove is going to be to clear up any and all headaches that just got caused by those of us seeing that there were 3 different definitions of smoothness for maps between Froelicher spaces. Yeah, instead of tearing your hair out because you have to check 3 different potential types of smoothness, don't, because they are all the same for maps between Froelicher spaces. So let me demonstrate that now with this page. I'm very happy that I managed to fit this on a page, though I had to make some economic decisions in some places. All right, so proposition 1, all of the definitions of smoothness are equivalent for maps between Froelicher spaces. So first, let's assume that F is a Serow smooth map. And what that means, based on the definition from the last piece of paper, was that for any plot that I gave you from X's plot family, the composition with F is in Y's plot family. However, by the definition of Froelicher structure, being in Y's plot family means that any composition with some C from Y's coplot family is going to be smooth. That's because Froelicher structures are smoothly maximal with respect to each other. So that means that F is a smooth map, because all it takes to be smooth map is that for any composition of P from X and any composition of C from Y, we end up getting a smooth map, which is exactly what we ended up getting. All right, so now we assume instead that F is Sikorsky smooth, and it's going to look exactly the same. So once again, that means that for any coplot from Y structure, the composition on the left side is a coplot for X's structure. But by the definition of Froelicher structure, that means this guy composes smoothly with any of the plots in X's structure. So this whole composition is smooth, and that's for any P from X and then for any C from Y, which is the definition of Froelicher smooth. So again, F is Froelicher smooth. So for the last one, assume that F is in fact Froelicher smooth, and that means that for any plot in X's plot family, and for any coplot in Y's coplot family, the map P into F into C is going to be a smooth map by the definition of Froelicher smooth. However, by the definition of Froelicher structure, and smooth maximality means that because this composition is smooth and P exists in this structure, our Froelicher structure, this map F composed with C, or C composed with F, has to exist in our coplot structure for X, and F composed with P has to exist in the plot structure of Y by smooth maximality. Just because this map is smooth, that means I'm composing this guy with someone from Y's, I'm composing someone here with someone from X's structure, plot structure, and I'm getting something smooth by Froelicher definition. That means this guy has to be in X's coplot structure, and the same thing for the other one. That's what smooth maximality gives you. So super straightforward. Once again, I think I've mentioned this a couple times now. The reason why I wanted to start everything off from these definitions is that everything is going to be super nice and simple and easy to follow, as opposed to when I talked about smooth manifolds. Just talking about the smooth structure of a smooth manifold, I had to introduce an equivalence relation and do a whole lot of proofs relating to that, and do a whole lot of work just to prove that like one thing made sense, and that was just going to keep happening over and over and over again. I can circumvent a lot of that. Some of it's still going to happen eventually, but I can circumvent a lot of that with this stuff because it's sort of down at the bottom of what it means to be smooth. Being a smooth manifold is much higher up. It's much more complicated structure. All right, so there you go. Headache assuaged. There is really only one type of smoothness for Froelicher structures. So you're not at all going to run astray just by calling maps in general smooth, because if they're maps between Serow structures, Serow spaces, they can only be Serow smooth. If they're maps between Froelicher structures, they can only be if they're maps between Sikorsky spaces, they can only be Sikorsky smooth. And if they're maps between Froelicher spaces, you can check whatever you want, and it doesn't matter. Now that we've gotten rid of that ambiguity in our set of definitions, let's talk about some examples of maps that are always smooth, like I promised. So what you probably expected if you've worked with maps before, or the smooth maps and testing whether or not they're smooth, the identity map is a smooth map. And this is going to be pretty easy to prove, as you can see. It's one line, or almost one line. I could write it down shorter. But I kind of want everything to come through easily on the camera. Or excuse me, write down smaller, but I want it to come through easier on the camera. But anyway, so the identity map is smooth in any of the three definitions. And to see that, for Serow smooth, so assuming we're talking about a identity map on a Serow space, let P be any plot in that Serow space's plot family. Then obviously when I compose the identity with P, I just get P back, because the identity doesn't do anything. And so that has to be in X's plot structure again. That's where I chose P from to begin with. But if I can compose you with a plot to get the plot in your codomain space, then that means you have to be Serow smooth. So by definition, the identity is Serow smooth. Likewise, I can take any, I chose Y this time. If Y was a space that was a Sikorsky space. Oh no, I should have chosen the same things here. There we go. I've got to do some on-spot corrections. All right, so let C be one of Y's coplots. Then obviously composing C on the left with the identity just gives me C back again. He's still in the coplot family. That's where I chose him. So that means he has to be identity has to be smooth because he takes coplots to coplots. That's all it takes to be Sikorsky smooth. And I wrote it all as one word here because I forgot to put a space there. All right, last one here. Let me get a single plot from P structure and a single coplot also from P structure, from X structure, and a single coplot also from X structure. Same thing here because it's the identity. It's between the same object. Then this map that I get by composing the coplot from X on one side and the plot from X on the other must be exactly the same as just composing a coplot with a plot from X, which by definition of a Froelicher structure must be a smooth Euclidean map. Therefore, this composition is a smooth Euclidean map, and therefore that means that the identity has to be Froelicher smooth. So, pretty easy. The identity is smooth in each definition. All right. On to another cheap and easy one. This time, because we've actually got a lot of axioms that essentially just give it to us for free, though that should always essentially be the case. Smoothness should always sort of incorporate this notion that constancy is like the ultimate type of smooth map. You can't be more smooth than being constant. So constant maps are smooth no matter what definition you choose. And if you ever come up with a more abstract definition of smoothness, constants better be a smooth map. Otherwise, it doesn't really make a whole lot of sense. Okay, so let F be a constant map, any constant map between spaces X and Y. For our first assumption, we're going to assume Serow spaces. And let P be any of X's plots. Then the composition of some map with a constant is a constant. So because of axiom 1 of the Serow spaces, any constant map is contained in a Serow structure. So that means that this composition has to be contained in Y's Serow structure. So that means that F is smooth by definition, or Serow smooth by definition. So now, if switch over to Sikorsky spaces and Sikorsky's definitions. Let C be any one of the coplots on Y, and if I compose it on the left with F, still a constant here, I still get a constant. I'm just plugging the same value into C every single time, I'm still getting a constant map. And by the definition, by Sikorsky axioms actually, for the first one again, I get to know that this is automatically one of the coplots in X structure. So therefore F is Sikorsky smooth by definition. Last things last, if I chose a plot and a coplot, and then I composed it on either side with F, it's still a constant map, nothing's changed. And if I have a constant map between Euclidean spaces, that guy, like I said before, he's the ultimate type of smooth map. It's super easy to check in a Euclidean space because you can take derivatives, and go ahead, if you don't believe me, go try taking the derivative of a constant map sometime. You'll find it to be very, very, very smooth. So, constants are in fact Froelicher smooth as well, because when I compose them with any choice of plot and coplot, I get a constant map between Euclidean spaces, and that is smooth. So the definition is satisfied. So we get constants too. Identities, constants, what else? We get, I think I might have covered this last time when I was in smooth manifolds, but we also get projections. So that is from products of spaces, Serow, Sikorsky, or Froelicher. Projection maps are going to necessarily be smooth. That one is almost exactly identical to the identity case. So if you feel like doing an exercise, go ahead and give that a puzzle out, or if you don't believe me. But if you do believe me that it is essentially just like doing the identity one, then go ahead and believe me that whenever we take the projection down from any number of product spaces down to one of their factors, that is also going to be smooth, no matter what definition we choose, which is nice. So these are a whole lot of different types of maps that we can automatically know that they're smooth, and we can potentially build other maps. That's the next thing. Next thing is building, exactly that, building other maps. I've told you examples of a couple of maps that are smooth, but say I give you some smooth maps, and how do you go on building new smooth maps out of them? Well, first thing we're going to get to is, it's probably going to be the last thing that I am able to work on today, just because I kind of want to keep this video shorter and just do more shorter videos. The last thing that I'm going to cover here is that composing smooth maps from any one of the definitions will give you a smooth map. So in that way you can use two smooth maps as long as their codomain and domain are appropriate, and compose them in order to get a new smooth map. So a way of building these things. So let's see that on the next piece of paper. All right, last proof for today, and a little bit of cleverness here. We get to use something that we've proven already. So composition preserves any and all sort of smoothness that we have defined so far. That is, if I take two maps that are the same sort of smooth and compose them together, then I get another map which is also smooth. Okay, so to see that, let's assume that I've been given a pair of functions, f and g, where I've got the domain and codomain of them picked out right here. And let's say that they're both Serow smooth. Then f Serow smoothness means that for any plot on its domain P, I can compose it with f in order to get a plot for y. But g smoothness means that for any plot for y, like this one right here that I just made, I can compose to get a plot for z. So this long string here is a plot for z, and that is exactly what it means to be Serow smooth. I took any plot for x, and I wound up with a plot for z for this fellow, using that composition. So that composition there is Serow smooth. Same sort of thing for Sikorsky. If I'm given that same sort of pair, and I assume that they're both Sikorsky smooth, then I've got plots now or coplots rather, for z, and whenever I compose it with g, Sikorsky smoothness of g guarantees me that this is a coplot for y. But by f's Sikorsky smoothness, whenever I compose a coplot for y with f, I get a coplot for x, but that's exactly the statement that I need to show that G compose F is Sikorsky smooth. So that thing is also Sikorsky smooth. And then instead of having to do another argument for the third case, remember that we started out by proving that Sikorsky and Serow and Fröhlicher smoothness are all equivalent for maps between Fröhlicher spaces. So what that means is if I assume that I have a pair of F and G that are appropriately chosen again, and they are Fröhlicher smooth, then they're also Sikorsky smooth. And if they're Sikorsky smooth or Serow smooth, it doesn't matter. If they're either one of those, then either one of these arguments apply up here, so their composition has to be Serow or Sikorsky smooth. But remember, Serow, Sikorsky, and Fröhlicher smoothness are all equivalent on Fröhlicher spaces, on maps between Fröhlicher spaces. So if their composition is either Sikorsky or Serow smooth, then their composition is Fröhlicher smooth. So the composition is Fröhlicher smooth as well. And that's a little bit of cleverness. All right, so that's what smoothness means to be, that is what it means to be smooth, rather, for maps between Sikorsky spaces. It's a whole lot easier to get there and a whole lot easier to make sense of than talking about smoothness between manifolds, because sort of, I keep saying this, but manifolds have a lot of additional structure, and it's kind of, they're built sort of backwards. What you want to be able to say, what John Milner says, for example, when he's writing topology from the differential viewpoint, he only talks about the extrinsic definition of manifolds, and it's so he can get the shortcut around having to come up with a definition for diffeomorphism between abstract spaces. He just doesn't do that. He says, take any subset of Euclidean space, which is diffeomorphic to some open subset of Rn, and he calls that an N-manifold. And that's something you can do because he's only talking about things that are already in a Euclidean space, where smoothness makes sense as something to talk about. Normally, though, when you're talking about the intrinsic definition of a smooth manifold, you start with a topological space, then you give it an atlas, then you give it a smooth atlas, which we talked about before, and that's how you make sense of smoothness. But that already you have the idea of this space and maps into it, and you have to keep throwing new things at it in order to get the idea of smooth. It would be really nice to be able to start with smoothness, and that's what we're doing here. The first thing we can do when we're talking about maps between any one of these spaces is talk about what it means for them to be smooth. Because of that, we can now also define diffeomorphisms. So we'll do that next time and talk more about it. But diffeomorphisms, they'll just be bijections whose inverse and themselves are also smooth. And then that gives, for instance, a super cheap, easy definition of manifold. It's just going to be a Serow, Sikorsky, or Fröhlicher space whose every point has a neighborhood which is diffeomorphic to Rn. And I'll show that at some point. I'll show that's an equivalent definition for manifold. But there's a whole lot of other things that come out of this change, of moving on to a slightly more abstract but fundamentally simpler and less complicated notation for smooth spaces. So we will explore this some more, and I will fully resolve my comments that I've made about my definitions and Sikorsky and Fröhlicher's definitions, but I will do that some other time, and I will try to be a little bit quicker about it this time. I was holding off because I wanted to settle those things, but there are a lot of things that I can say that are not controversial. So I'll do those first, and I'll have that working in the background. So hopefully see you all again soon. Enjoy yourselves some differential topology.